Hello, and today we are taking notes on forces and free body diagrams. If you'd like to take notes on your own, you're more than welcome to do so. I have also posted the fill in the blank notes, and I will be highlighting the key points for you to follow along with. All right, first thing, what is a force? A force is a push or a pull that acts on an object. So it could result in an object moving, but it doesn't have to. All right, so it can move. Forces can cause a resting object to move or accelerate, and that is caused by changing an object's speed or direction. Remember, acceleration can be either positive or negative. Sometimes the negative acceleration is referred to as deceleration or the braking speed. It doesn't matter what you refer it to, positive acceleration, negative acceleration, or deceleration. Okay, so force can cause something to speed up, such as this dad pushing his son on the bike and causing the son to speed up. Forces can also act to slow something down. So we have a moving train, and Superman then comes along and applies a force in the opposite direction to slow the train down. And if you can see these arrows that are drawn in here, you guys will be getting practice drawing those on things called free body diagrams. And these forces these arrows just represent the forces that are moving in the different directions that are shown here. And you will add up those forces to see what the net force is and the resulting motion of the object. Forces can also cause something to change direction. And remember that if we have a direction as well as a magnitude, that means that we have a vector quantity. So all of these forces, if they're changing directions or involve direction, they are vector quantities. Okay, and with forces, we will come calculation to figure out how much force was actually applied. And the units with force are newtons. This is a brand new unit. It is new in a few ways, actually. One, that we haven't heard of newtons before, and that this unit is made up of smaller units. So here it is, that 1 Newton is equal to 1 kilogram times meters per second squared. Quite a mouthful, but let's dissect that a little bit. That, make that a little bigger. 1 kilogram times meters per second squared is equal to 1 Newton. So we already talked a little bit about acceleration in this video, and that is why. So within the units of newtons, we have the acceleration formula, meters per second squared. So when we are looking at forces, which are newtons, we are really looking at the acceleration or deceleration of an object as well as the mass. So a newton is the mass times the acceleration. All right, and causes of motion. Motion is caused by a force. It can be a push or pull, like we said on the first couple slides, and that results in unbalanced forces or balanced forces. I said that in the opposite order that I highlighted. Sorry about that. But balanced forces keep an object at rest. So if you have maybe you have two twin little brothers and they're pulling on either side of you, and let's say they can pull at the exact same force, you're not going anywhere. But maybe you have one little brother and then one older brother pulling on either arm of you. You're probably going to go in the direction of the older brother yanking on your arm because it was an unbalanced force. He was much stronger than the younger little brother. All right, here's some more examples with pictures. So we have a truck that is staying still, It has a force of 100 newtons pushing it forward, but a force of 100 newtons also pushing it backward. So that truck is not moving. But in the second picture, we still have the 100 newtons of force pushing that truck forward, and now we only have 60 newtons of force holding it back. So this truck is going to move in the forward direction due to unbalanced forces being applied. Down here we have tug of war examples. As you can see in the first one, nobody is winning this just yet. They have equal amounts of forces being pulled on either side. But maybe the game went on for a little bit longer, and the team on the left, the side, now has 400 newtons of force pulling, and they're probably going to win this battle because the forces are unbalanced and going in the left direction. All right, now more about forces. Force is a vector quantity, as I said earlier, because it does have magnitude and direction. Okay. When you guys start drawing out these force vectors, the direction of the arrow represents the direction of the force being applied. I'm going to go back to this one. So how the 400 newtons of force being applied from the team on the left, that is why the arrow is pointing to the left, because that is the direction they are pulling. Right? And also when you guys get to drawing these, the length of the arrow will represent the strength of the force. So if you have a greater force, it's going to be a longer arrow versus a lesser force is going to be a shorter arrow. And to determine the net force to see if something is actually going to move, you are going to combine all of the forces together, and that is called the net force. It will tell you the direction and the magnitude that the object will go in that direction. And we represent these on things called free body diagrams. We'll have some examples of those coming very shortly. Here's pictures of the different force arrows. So balanced forces have a net of 0, so like C at the bottom, no change in direction. Whereas unbalanced forces, they are acting on an object, and A and B are both unbalanced forces. So we have unbalanced force in B, we have a greater one right here. Therefore, the difference of those two will cause the object to go left. For A, we have two forces acting in the same direction. So we add those together, and the result is going to the right with the magnitude of both of those together. So now, what is a free body diagram? Here we have a cow and two girls pushing on the cow. I don't think that's a great idea, but kind of a funny little picture. So the two girls are applying a force of 34 newtons east, and let's throw those in there. 34 newtons east and 50 newtons west. Oh, sorry. So as you can see, the 50 newtons west is a larger arrow because it is a larger force compared to the 34 newtons. Therefore, what direction is the cow going to move? And surprisingly, it is going that little girl on the right that is saying, "Let's go steak." She is going to cause this cow to move to the left at about 16 newtons. And how I found that 16 newtons was by taking 50 newtons and finding the difference of 34. Okay, so here's another example of unbalanced forces, but actually applied to a free body diagram. And unfortunately, the question is already answered for you. Sorry about that. The PDF did not include the first slide of this. So the two boxes that are already circled are the unbalanced forces. And you can see that the arrows of each of them are unbalanced. And I will highlight the ones that are larger. The one that is in the center, the two arrows are supposed to be the exact same size, therefore they are balanced and that object is not going to move. Okay, so now we got a large list of the types of forces. Please pause the video and read through those. You will need to know of them and know when to apply them. I don't think that you need to necessarily memorize the definition of them because a lot of them are really self-explanatory. For example, F gravity, the friction of gravity. I hope that you know that force can only be applied if there is gravity. And friction, F friction. There are a lot of different types of friction, but I think generally people know what friction is. Something or a force exerted on a surface, and it causes something to stop moving, like when you are driving in a car and putting on the brakes. The friction of the road also helps the car come to a stop. Okay. But in free body diagrams, you will need to label your arrows with all of the things that I highlighted. So this is a really good slide to maybe take a screenshot of and save for later when you are doing those free body diagrams. Okay, so I've already talked a little bit about net forces and what they mean, but how you calculate it is with this equation right here, with just adding up all of the forces. All right, and let's do an example. So this first one I did for you, and the next ones you guys are going to get to do, you're going to get to try it out by pausing the video and doing it on your own. So what is the net force on a box that is pulled west with a force of 200 newtons and pulled east with a force of 450 newtons? All right, so there's something new that I need to point out before we continue, and that is the compass right here. So north and east, or up and right, are considered positive. Left or west and down and south are both negative. So when you are adding up forces that are going up, down, left, right, we need to identify if they are positive or negative based on this. Okay. In my example earlier, finding the difference of the two will tell you the direction that it goes also. Really same thing applied here. We just had not gotten to this directional yet. Okay, so the net force of the box ends up being 250 newtons positive, so 250 newtons to the right or east. That is because there is a greater force being pulled in that direction. And when we are calculating it based on the positives and negatives in our directional to the right, the 200 newtons will be our negative since it is west or to the left. All right, why don't you guys try this one out? What is the net force on a box that is pulled west with a force of 3 newtons, pulled to the east with a force of 20 newtons, pulled up with a force of 6 newtons, and pulled down with a force of 6 newtons? And the diagram is right below the question. Pause the video and calculate what the net force is for this box, and then identify where the box is going to move. Don't forget to use the different directionals and apply the correct positive or negative depending on the direction it is going. So pause your video now. Okay, time to check your answers. So here's the calculation. The 20 newtons plus -3 newtons plus 6 newtons plus -6 newtons. So you basically don't need to talk about or even incorporate the 6 newtons up and 6 newtons down. That just basically is telling you that this object is not sinking below whatever surface it is on, nor it is floating in the air. Those two things are balanced. So if this box was sitting on a table, it's just sitting on that table, not crashing through or floating. But it is going to be moving right or east because it has a greater force of 20 newtons pulling it in that direction. And it will go 17, be pulled with 17 newtons east. Sorry if I said 20 earlier. Okay, so we just said two examples of how unbalanced forces make an object accelerate. But what happens when they are balanced, like we have in this example? So 68 newtons in the east-west direction or left-right direction, that gives us a net force of 0. And you could always double check that by actually punching it in. So we'll have -68 newtons plus 68 newtons, which equals 0. So anytime you get a 0 for your forces, know that your object is stationary. And we also refer to this as stationary or balanced as the object being at equilibrium, not slowing up, not speeding down, and not changing directions. It is a motionless object. The object doesn't actually have to just be motionless. It could be moving at a constant velocity, because if it's moving at a constant velocity, it still has it is still not speeding up nor slowing down. It is just moving in that direction at a constant speed. Right, and that is actually a big thing that confuses students. That equilibrium is not, it means motionless, but it also means that it is moving at a constant velocity. All right, now we're going to get some practice problems with you guys actually drawing the free body diagrams from a description. You will have some of these on your worksheet later. So given the scenario of a rightward force being applied to a book in order to move it across a desk with a rightward acceleration, you do need to consider frictional forces, but neglect air resistance. All right, so when you guys are drawing this free body diagram, you will be drawing arrows off of the box, just like we saw right here. And notice that the arrows are always pointing away from the box, okay? So make sure that you do that as well. There we go. All right, pause the video, try it out, and press play when you're ready to see the answer. All right, now I'm assuming this one was probably the most challenging since it was your first try at this. Let's see how you did. So the object is moving, and it is moving with a rightward acceleration. So as you can see, my force applied, which was just somebody pushing the book, they were applying a force. Has the largest arrow going toward the right. And there is still friction though, because it said to make sure to consider the frictional forces that are trying to slow the box down or the book down, but because it's specifically said that it is moving, it is not going to be an arrow that is going to be equal in length because it is not slowing the box down very much. And then we have the normal and gravity forces. So the normal force is the desk. It is just sitting there. It is not, the book is not falling through the desk. And then gravity is what is keeping it from floating up in the air. So those two forces are balanced, and the arrows should be the exact same length. And then the unbalanced forces are the applied and friction ones, and that is why the book is moving to the right. Let's try out one more of these and then we'll be done. All right, so hopefully this one will feel a little bit easier now that we had an example like this under our belts. But try out a car is coasting to the right and slowing down. Pause the video and draw out your vectors. Okay, let's see how you guys did. All right, so something should look very familiar, and that is the normal and gravity force. So just like the book wasn't crashing through the desk or floating in the air, the car is not going below the Earth's crust, nor is it floating through the air. That would be really cool, but it's not happening. So those forces are yet again balanced, keeping the car on the ground. But the friction force is causing the car to slow down. This is unbalanced. It didn't say that the car was still accelerating. It just said it was coasting and slowing down. It didn't say that brakes were being applied, so there was no applied force. It was only the friction of the road causing the box or the car to slow down. All right, and that will be it for today's lecture. Thank you guys for listening, and let me know if you have any questions.